All right, great. Thank you very much, everyone, for tuning in for this week's Foundation Probability Seminar. Today, we have the great pleasure of having Jason Konek to come and speak with us about his recent work on the accuracy for sets of almost desirable gambles. So Jason is at the University of Bristol, and previously he completed his PhD from Michigan with Jim Joyce, and you were at various places before Bristol. And I just looked this up. In fact, I'm sorry, you're at Kansas State and Kent, and you're right now, but working on you're leading this very big project on the epistemenic utility for understanding imprecise probabilities. That's very interesting. So we're very happy to have you with us, and please take it away.
Good, thank you. Thank you for having me. So I am going to try to tell you a version of a probably familiar story. Many of you will know, sort of starting with De Finetti's work on coherence to kind of concepts of coherence. There was a move in the late 90s to take De Finetti's work, showing that a set of provisions, in order to avoid being dominated by another set of provisions, in the sense that it is assigned a lower penalty according to the Breyer score, a particular loss function. Those provisions must be probabilistically coherent. And Jim Joyce and others since then took the same kind of framework and both generalized it and gave it a different kind of philosophical interpretation. So where for De Finetti, the Breyer score was used to provide a practical loss to an agent's provisions, announced provisions. So she provides forecasts for some number of variables, and then the outcome, the actual values of those forecasts are observed, and then on the basis of the squared difference between her provisions and the actual outcomes, you sum up those penalties, and that's the Breyer score. And the hope was to kind of have a loss function that incentivized forecasters to, well, when Breyer kind of announced this, developed this in the 50s, we wanted to incentivize forecasters to announce their true provisions. So it was used primarily for elicitation. De Finetti showed that in order to avoid dominance by the Breyer score, your provisions had to be probabilistically coherent. Joyce argued that the Breyer score actually satisfies a number of properties that makes it a good measure of the accuracy of the estimates that the agent is announcing. And so aimed to provide a justification for probabilism, or for having coherent provisions on the basis of their epistemic properties. So the thought was, we're going to outline a large class of loss functions that intuitively have properties that make them good measures of accuracy of estimates. And then we're going to show that on any of these loss functions, if you announce if your provisions are incoherent, then you have this vice, this epistemic vice, namely that there's some other set of provisions that you could have had, some other set of estimates that you could have had that are guaranteed to be more accurate. And the thought is that is a purely alethic flaw, and it kind of providing this argument in full generality elucidates our reasons for having coherent provisions. Okay, what I want to do here is extend that kind of argument to coherence for sets of desirable gambles. So I want to give you some scoring rules that capture alethic, two types of alethic error that I think that sets of almost desirable gambles can be subject to, and show that you have to your set of almost desirable gambles, the one that captures your opinions, must be coherent on pain of accuracy dominance. Okay, so this framework may or may not be familiar to all of you. I hope it is not too foreign, but it's a fairly general imprecise probability framework, sets of almost desirable gambles. And the basic idea is we are going to say, collect up all the gambles that you think are at least as good as the status quo, so almost desirable. That will, if your judgments about desirability are coherent, satisfy these 5 axioms, that will include all of these gambles over here. So this, for example, at 5.2 is the gamble that pays out, let's say this is a gamble on heads or tails, it pays out 5 quid if the coin comes up heads, 2 quid if it comes up tails. So these are all these gambles in this region are all the gambles that sometimes pay out a positive amount and never pay out a negative amount. And if you satisfy the rest of these axioms, what we end up having is that your judgments of desirability, the ones that you think are at least as good as the status quo, they form a closed convex cone. Now, this is a fairly general kind of framework for modeling your uncertainty. We can capture in this framework precise probabilities. Precise probabilities correspond to closed half spaces, but there are lots of sets of desirable gambles that will be coherent, that don't correspond to precise probabilities. It's strictly more general than precise probabilities. More general than coherent lower probabilities. We're going to work in this class of frameworks, which are all equally expressive if coherent. Coherent lower provisions, closed convex sets of probabilities, coherent sets of almost desirable gambles or strictly desirable gambles. The difference between those two being whether we include the boundaries here as in the set. If we're talking about almost desirability, then this is going to be closed. So these boundary points are in our sets. If we were talking about strictly desirable gambles, then those would always be open, or equivalently partial almost preference relations. Now this is, as many of you will know, not the most expressive framework. I mean, sets of desirable gambles, not sets of almost desirable gambles. Those are more expressive than almost desirable gambles, as are partial preference relations and choice functions and rejection functions. The reason we're not using those, starting directly with those frameworks, is twofold. One, coherent lower provisions, while not the most general, are still significantly more general. So the difference, I think, in generality between, say, precise probabilities and coherent lower provisions is huge. The difference in generality between, say, almost desirable gambles and sets of desirable gambles has to do with boundary behavior. which can be important, but is less of a big departure than from here to here. But the real reason is the tools that we're going to use to think about accuracy here they're not going to be sensitive to differences on sets of measure 0, like boundaries. And so we're going to try to just get as far as we can with these tools, and then these tools are going to have to be made more sophisticated in the future if we want to get similar kinds of arguments for coherence for sets of desirable gambles or for choice functions or what have you. But it's a starting point. This kind of work for IP hasn't been done to date, so we're gonna start with a reasonably flexible framework, but not a fully not full generality. Okay, so why is any of this important? Why is giving an accuracy dominance argument for coherence important? Well, I think it's important for the same reason that it was important in the precise case, maybe even more pressing in the imprecise case. So here we have and this will be familiar to all of you, but just to reiterate a statement from Walley, we can't justify coherence on using considerations of sure loss. I mean, you can avoid sure loss while violating coherence. Some violations of coherence amount to violations that open you up to sure loss, but others don't. So coherence is a stronger criterion than avoiding sure loss. It amounts to working out, in some sense, the implications. Here, Walley is talking about lower provisions, but it amounts to working out the implications of some assessments that you've already made. Somehow implicit in some judgments of desirability that you make about some gambles, they commit you to certain other judgments of desirability for other gambles. So if we go back here, the thought is, for example, if we just look at D3, if I judge this gamble desirable, well, then I have to judge everything on this ray desirable as well. Somehow that's implicit in my earlier commitment. But if I violate that, say by having this be open here, I haven't opened myself up to a sure loss. I just, in some way, haven't teased out the implications of my earlier assessments. And what we want to know is, what's so bad about violating coherence if you avoid sure loss? And the answer that we're going to give is even if you are not susceptible to sure loss in utility or money, you are, if you violate coherence, subject to sure alethic loss. There's some other set of almost desirable gambles, if you're not coherent, that is guaranteed to be more accurate than you are. Now, again, this is only going to be coherence up to a set of measure 0. So this kind of violation that I had here isn't going to be the sort of thing that we're going to be able to impugn. But we could have, for example, have had a curve boundary here. And this fails to be coherent. It's not a closed convex cone, but it doesn't open you up to sure loss. And the question is, what is so bad about having a set of desirable gambles like that? And the answer is that I'm going to provide here is that it's accuracy dominated. Okay, so start with some background on scoring rules for precise provisions, and then I'm going to take inspiration from a characterization provided by Shervish to give us, to help construct scoring rules for sets of almost desirable gambles. So an inaccuracy measure or a scoring rule is going to be a function that takes a pair of what philosophers call credence functions. You might think of them as assignments of estimates to indicator variables or indicator gambles, assignments of truth value estimates to propositions. But it's going to take a pair of both a point in your sample space, which is going to fix the truth value of all the propositions that you have estimates for. So we'll call those worlds. Take a pair of a credence function and a world, and it's going to spit out an alethic penalty. A penalty that penalizes the credence function on the basis of how far its estimates are from the truth value of the propositions that it assigns estimates to. So 0 if false, 1 if true. And what makes it an alethic loss function is that it has certain properties that guarantee that it is penalizing on the basis of distance from the truth. So these are going to be properties like truth directedness. So if I have two sets of truth value estimates or precise provisions for a bunch of propositions, and one of them is uniformly closer to the truth values of all of the propositions, so that the distance between B's estimates, so something like 0.7, and the actual truth value is that estimate is closer to the actual truth value than C's. If that is true for all propositions, then our loss function better assign B a smaller loss than it assigns to C. That is part of what makes it an accuracy, a measure of accuracy. It's a certain kind of loss function that cares about distance from truth. So that seems like truth directedness is one non-negotiable constraint on measures of accuracy. The other properties are less obviously fall straight out of the concept of accuracy, but strict propriety in particular is crucial to every result that utilizes scoring rules in what in the philosophical community has come to be known accuracy-centered epistemology. Every result in accuracy-centered epistemology relies on strict propriety. What does strict propriety say? It says every probability function expects itself to be more accurate than any other probability function. Sorry, than any other function, period. Every probability function thinks, well, I don't have incentive to move to different provisions unless I get evidence that forces me to update my credences. I think, given the evidence I have, I think I'm doing best. I expect myself to have the lowest inaccuracy possible. And in practice, many of the scoring rules that people use when they focus on particular scoring rules are additive, in the sense that there is a local score that penalizes an individual provision based on the actual value of, I mean, you can do this for variables and provisions quite generally. The focus in accuracy-centered epistemology has been on truth value estimates and indicator variables or propositions. But additive scores go through, penalize each estimate and then sum up those penalties to get the overall degree of inaccuracy of the entire set of provisions. That obviously is only going to work sensibly when you have a finite set of propositions that you're working with, but most people in the literature are assuming that. Okay, so all the popular scores, the Breyer score, log score, spherical score, are all examples of these additive, strictly proper, truth-directed scoring rules. Now, I mean, I'll talk a little bit about the motivation for this. One useful result, so there are a number of characterizations of strictly proper scoring rules. One useful characterization comes from Shervish. This is a bit of a simplified version of Shervish's actual result. It's a little bit more nuanced than this, but Shervish shows that every continuous additive strictly proper score takes this kind of form. The local thing that penalizes an individual provision it takes this integral form. So there's some measure that gives you, when you integrate with respect to the measure in the ways indicated here, give you back the local score in the case where the proposition is true and false, respectively. Now, this falls fairly straightforwardly out of continuity and strict propriety. I will go through the reason that I think the construction is attractive in a moment, but I just wanted to highlight it here because you will see that our scoring rules for sets of almost desirable gambles take a very similar form. Okay, that's really all I want to say about scoring rules, although I realize that folks that are following along may not be particularly familiar with one or another part of this setup, so maybe now is a good time to pause and ask clarifying questions before we move on to the new stuff, since this is all kind of background stuff.
I do have one, Jason.
Yeah.
Not about the scoring rule part, but just, I guess this is just to clarify, when you say coherence, what you meant was specifically those 5 axioms.
Yeah, so these are the axioms for coherence for almost desirability.
For almost desirable gambles, I see. Yeah. So
yeah, we're not going to have, for sets of desirable gambles rather than almost desirable gambles, we're not going to have D5 because D5 forces boundary points to be in the set. Right. We're just going to have this, and then we're going to replace D1 with 0 is not an element of D. So if we were talking about desirability, yeah, we'd have a slightly different axiomatization, but.
I see. So when you said on the second page, basically that avoiding Shor loss is necessary, but not sufficient for violating coherence, what you meant was for a Shor loss in terms of how do you actually formulate Shor loss in this context?
Yeah, so I mean, Shor loss in this context amounts to judging as desirable some gamble in this region.
Got it.
And obviously there are all sorts of wonky ways that we can, you know, have a set of gambles that doesn't include anything in that region, but violates the axioms of coherence. Because the axioms of coherence in this case force it to be a closed convex cone. So there are lots of ways to do that. Now, I mean, there are going to be different concepts of coherence for different frameworks. In the quote we were talking about from Walley, he was talking about coherence for lower provisions. But we're going to have axiomizations for almost or strictly desirable or just desirable sets of gambles. We're going to have corresponding axiomizations for preference relations. So you can kind of move interchangeably between preferences and desirability. So in our case, we're going to have a weak preference relation that says I weakly prefer X to Y, and that's going to be true just in case I judge X minus Y to be almost desirable. And if we were working with a normal preference relation, then we would have a different axiomization for the preference relation and a different corresponding axiomization for the set of desirable gambles that it generates. But I mean, I think most people think of this as a kind of we're just doing the logic of desirability. I mean, we've got some concept of desirability. We've got some axioms that make precise our notion of desirability, and then we're going to see what the implications are for it. We're going to see, you know, if I make a certain set of assessments, I want to be able to say do natural extension, which is going to give me the weakest set of desirable gambles that is coherent and contains my assessment.
So
in our case, we're trying to give not just do logic of desirability to show that they're motivated. We can motivate those same axioms in another direction on the basis of accuracy considerations.
I think maybe what I'm about to ask, if it makes sense at all, the answer may be buried in what you just said. Let me ask this question, and you can tell me if this is even a sensible one to ask. You define on the first page the coherent set of almost desirable gambles. Is there such a thing as an incoherent set of almost desirable gambles? I'm trying to get a sense of what is it that makes something an almost desirable gamble, and what makes it coherent versus not coherent. So in the 5 axioms that you have, what are the things that are specifically saying that these things are coherent versus otherwise? If I take it for granted that we're dealing with almost desirable gambles, does that make sense?
Yeah, I think so. I mean, there's any subset of, in this case, we're just looking at gambles on heads or tails. Any collection of gambles, in principle, could count as a set of almost desirable gambles. I mean, an agent could make the judgment that these and exactly these gambles are the ones that are at least as good as the status quo. Any arbitrary subset of R2 in this case. What makes it coherent is if that subset is a closed convex cone that includes the positive orthants. So here's a way to violate that. I could have what looks like a closed convex cone, but it, includes the positive orthants and doesn't include any strictly negative gamble. So I could have a closed convex cone that does include those. That would be incoherent, and that would be, in that case, you would be subject to a sure loss. I could also have, I don't know, say, this set of almost desirable gambles. which isn't subject to a sure loss. The natural extension would just be if this was actually just a half circle here, would just be a precise provision. But it's not, this original thing isn't coherent because there are gambles in my set such that if I took I multiplied it by some scalar, those things aren't in my set, and that's what makes it incoherent in this case. Or, I mean, a million ways you could do this if I had these and I didn't include the things in between, that would fail coherence. But it would still, in principle, be a set of, it would represent an incoherent agent's opinions, her judgments of desirability. Does that make some sense?
Right. Yes. Yes, I think so. Thank you.
Okay.
Jason, can I ask you a sort of follow-up question to Robin?
Yes, of course.
I think you mentioned this. I just missed it. What's the difference between almost desirable Dumbbells and desirable Dumbbells?
I mean, the difference in the concept is just whether something is at least as good as the status quo or better than the status quo. Strictly preferable to the status quo. I mean, I think it's standard to do this in terms of preference. So yeah, think of it in terms of strict and weak preference. I mean, you could tease out the behavioral implications where if I think it's strictly desirable, then if you just offer me that gamble, offer me a choice between that gamble and the status quo, and I think it's strictly desirable, then I'm going to take the gamble. If you offer me, if I think it's just weakly desirable, then I'm going to take the gamble if you sweeten it by any epsilon. But I'm not going to have a preference between it and the status quo when it's not sweetened, or I might not.
So it's not specified in the 5 axioms, right? So I was taking a version of Robin's previous question was, what happens to the definition if we just say we're defining a coherent set of Dumbbells? And it seems like, based on my understanding, coherence is just a closure condition, and that's what the 5 axioms are saying. So almost desirability is something that you say, okay, here are the Dumbbells that we're considering. They are almost desirable Dumbbells, but they're not captured by the 5 axioms. Is that the correct way of understanding it?
Sorry, can you repeat the question? I'm not sure I tracked the last bit of it.
So I took Robin's question. Part of the question was, suppose we change the definition saying, here we're giving the definition a coherent set of Dumbbells, if and only if. So we say a subset of Rn is a coherent set of Dumbbells, and a Dumbbell would just be a real valued function, if and only if it satisfies the following 5 axioms.
Sure.
And it seems like that's actually what's going on. And then by almost desirability, you are talking about, okay, here are the Dumbbells that satisfy some extraneous external conditions, but actually the 5 axioms are only giving you characterizations of coherence. Is that the correct way of understanding?
Yeah, I mean, I think the axiomization is meant to make precise a certain concept of desirability that you have in the background, or a certain concept of strict preference that you have in the background. I mean, take axiom D5 here. If it's, yeah, if I judge everything, any sweetening of it to be desirable, then I judge that thing, if I judge every sweetening to be almost desirable, then I judge the original thing to be almost desirable. If you were working with the concept of strict preference or strict desirability, that axiom wouldn't make a ton of sense. And yeah, I mean, I think that's the way in which the axioms are meant to explicate the concept of desirability at play.
Thank you. Thank you. Oh, I see. I was missing the obvious point, which is coherence notion is indexed to the kind of desirability that you're trying to axiomize.
Yes, yes, absolutely.
Yeah, sorry.
Yeah, I think
Thank you. Thank you.
that's absolutely right. Okay, good. Okay, so when we were talking about accuracy measures for precise provisions, there were, I mean, for additive measures, there were a few different steps to this. So one, there's somehow a comparison of the provision and the actual value. And then you get a penalty on that basis, and then you somehow aggregate those things. So, I mean, this first step where you compare the estimates to the actual value, we're going to need to do, if we're going to have measures of accuracy for sets of almost desirable gambles, we're going to have something that corresponds to the true value. But here, instead of talking about the truth full stop, we're going to think of in the precise case, the set of provisions that outputs the true values of the variables or the propositions in question as the perfect set of provisions to have at that world. And our analogous question in the set of almost desirable gambles framework is, what is the perfect set of almost desirable gambles at a given world? And then somehow we're going to want to penalize a set of almost desirable gambles on the basis of how much it diverges from that perfect thing. So the first postulate, the first ingredient to our scoring rules for sets of almost desirable gambles is this, what I call here a perfection postulate, that says the ideal set of almost desirable gambles at a world is given by this set. So it's all and only the gambles that actually pay out a non-negative amount, either 0 or a positive amount. Those are all the actually desirable gambles, or if you like, it's what God would judge to be almost desirable. So there's going to be a different one of these at each world or each point in our sample space. And we're going to penalize a set of desirable gambles, almost desirable gambles, for accuracy on the basis of how far it diverges from it, and then hopefully show that incoherence comes at the cost of diverging unnecessarily from these perfect sets, that there's something that's closer to every single one of them if you end up being incoherent. Okay, so choose a set, not necessarily coherent set of almost desirable gambles, so just some subsets of Rn. And the claim is that there are two types of alethic error that this thing might be subject to. Two kinds of mistakes you can make that collapse in the case of precise probabilities, but come apart in the case of imprecise probabilities. So one is a kind of generalized type 1 error, which might be familiar to you from hypothesis testing. And roughly, this is going to be a matter of making false judgments of almost desirability. So what we're doing here, what this is meant to capture, this FI, is the degree to which our set says false things, makes false judgments of desirability at world WI. So how are we doing that? Well, we're focusing on the things that this is just the complement, the set theoretic difference. So this is the set of things in D, but not in DI, not in the perfect set. So what are we doing here? intuitively we're choose a gamble if it's in D, but it's not in DI. So that is if we judge it desirable, but it's not actually desirable, or we judge it almost desirable, but it's not actually almost desirable, then we accumulate some type 1 error for making that false judgment. How much error we accumulate depends on how close to almost desirable that gamble is. So if it's actually undesirable, but we judge it almost desirable, but it's pretty close, we don't accumulate that much type 1 error. If it's really, really, really undesirable, I get negative 100,000 quid, negative 100,000 utils. Then I accumulate more type 1 error on that basis. Now, this I really think is just a heuristic. I think there's a better way to think about these things, in that that is in terms of a sort of potential or kinetic energy. So if we go back to the Shervish construction for a second, one way to think about what Shervish's representation theorem was giving us is accuracy in terms of kinetic energy. So think of, say we have an estimate of 0.8, a credence of 0.8, or a truth value estimate of 0.8 for a proposition, and the proposition turns out to be false. So here's our estimate, here's the truth value. How are we scoring that estimate? Well, according to Shervish, you can imagine, I don't know if you played Mario Kart, back when Mario Kart was a thing, but you can imagine there being little booster arrows as you go along this, and the further you get away from 0, the bigger the booster arrows become. And so the longer you're going along that track, the more energy you're picking up from these booster arrows. And then there's some underlying measure, mu, which shrinks or expands those booster arrows. So in this case, it's making this 0.3 booster arrow really big because there's a lot of mass here, and it's shrinking down this 0.6 booster arrow to something smaller. And the score that any strictly proper scoring, continuous additive strictly proper scoring gives you is the amount of kinetic energy that you have when you travel through this vector field. You're getting boosted along this vector field. It's the amount of energy that you have when you get to 0.8. And one way you can think of this is as like starting with the perfect thing and then becoming slowly more deformed, and the energy is kind of deforming you, and the inaccuracy that you have according to a strictly proper scoring rule is a measure of how deformed you are when you get that far away, where the deformation is given in terms of the energy that you've picked up. Now we're going to try to do something similar. What this is doing something similar for sets of desirable gambles, but instead of just starting with a truth value and moving away from that and picking up energy as you move away from that, now we're going to start with a perfect set of desirable gambles. So let's say it's true. So the coin comes up heads, and this is our perfect set of almost desirable gambles. And let's say I have some other set of almost desirable gambles whose boundary follows along here. Now, instead of moving a single provision, I'm moving the entire boundary away from the perfect boundary. And so I'm picking up some speed as I move this point of the boundary away from the perfect one. And I'm picking up some more energy as I move this part of the boundary away, and so on. And the amount of energy that, so I'm moving through a vector field as I move further and further away from actually almost desirable. These little boosters, which are given by these things, they're pushing me to pick up more and more speed. And again, I have some underlying measure that makes some of these little boosters bigger or smaller. But as a result of moving through this field, I've got some energy, some kinetic energy that I have when I get to this point, and that's my inaccuracy score. So it's very similar. The construction is very similar to the Shervish construction, although in this case, there's no property like strict propriety, or at least not one that I'm aware of, that is yielding this characterization. So we're starting with the construction. So in the precise case, we started with strict propriety, and then we were able to get this construction that yielded all the strictly proper scoring rules. Now we're just taking that construction as a kind of well-motivated way of constructing good measures of accuracy and using it to extend to the imprecise case. Okay, so these are all the gambles that are contributing to type 1 error. These are the things that we're saying are desirable, but they're not actually desirable. And then the other bit that we have to look at is the stuff that's in here. And that's the stuff that we're silent about, but we shouldn't be, because it's actually desirable. And the thought is there's a kind of generalized type 2 error that sets of almost desirable gambles are subject to. And we're going to measure that in exactly the analogous way. I have this little Jekyll and Hyde thing here because that's how I'm thinking about inaccuracy. We're starting at perfection and then slowly moving the boundary away until we have deformed it, and the energy that we use to deform it is our inaccuracy score. Okay, so type 2 error is being calculated in the same way using the same measure, except here we're looking at the things that, Before we were looking at the things that we judged desirable but weren't. Here we're looking at the things that are desirable, but we have not judged them desirable. So we're silent about them, but we shouldn't be. Okay, and then, so just all we've used is these set theoretic complements and some underlying measure to give us an accuracy score. I am assuming that this measure makes all of these integrals finite. This is something that we may want to relax in the future, allow inaccuracy scores to take infinite values at some places, but here I'm assuming they're finite. And then we're going to aggregate these two penalties somehow. And it should definitely be at least a weakly increasing function of the two penalties. I will make actually some more restrictive assumptions when we give the dominance arguments. But let me just briefly give you some what I hope are encouraging results that hopefully make you think that these scoring rules are kind of worthy of further investigation, that they're on the right track. So two facts about this class of scoring rules. One, if we aggregate the two scores by just summing them, summing type 1 and type 2 error together, and that's how we're calculating overall inaccuracy, those will always turn out to be strictly proper scoring rules. Okay, so that's one sufficient condition for generating a strictly proper scoring rule. And we can also, the framework is flexible enough that we can recover all additive strictly proper scoring rules. And so I won't go through the details here, but the point is, you end up with a big class of scoring rules, but they're flexible enough that you can always recover as a special case the strictly proper scoring rules in a fairly straightforward way. Now, but not all of these things are going to be strictly proper. In particular, the ones that sort of incentivize imprecision will not be strictly proper. One thing to note is that this gives you a kind of nice way of constructing non-additive scores, which might be useful for various purposes and which have not been really extensively explored in the literature. But because we're already running long, I will not dwell on that. Okay, so here's the main result. We've now kind of outlined a class of inaccuracy measures. We can use this to, at least in a special case, provide an accuracy dominance argument for coherence for almost the axioms for coherence for almost desirable gambles, sets of almost desirable gambles. So here's what I'm going to assume. For this one, we're just working in the simplest case, the two-dimensional case that we've been thinking about so far. So this needs to be generalized to the general n-dimensional case. I'm also going to assume that we're aggregating not just by summing them, but by taking some linear combination of the two penalties. So there's going to be some positive constants that I'm using to generate the overall inaccuracy, and I'm going to use the same constants when the proposition is true and when it's false. I am also here, I think this is inessential, but for the version of the proof that I am discussing right now, assuming that the underlying measure respects a certain kind of symmetry, so that in particular, the density function that generates the underlying measure treats x and y and negative x and negative y exactly the same. So what this amounts to, saying, for example, that this gamble, which say the proposition is true, so this is in fact not desirable. This gamble contributes in exactly the same way to the overall type 1 error as this gamble does to type 2 error. So, getting it wrong, saying that something that's going to cost me 3 quid is desirable, that contributes to type 1 error in exactly the same way that failing to judge a gamble that pays out 3 quid contributes to type 2 error. When I'm silent about that second gamble, that contributes to type 2 error in exactly the same way. I think we can relax that assumption, but for proposition, for proposition 3, for one part of it, I'm using that. Okay, so the result is that if a set of almost desirable gambles is incoherent, then there's some other set of desirable gambles that accuracy dominates it. That is, according to, and this is true for any scoring rule. So if it's incoherent, then for any scoring rule in our class, there is some other set of desirable gambles that is guaranteed to do better according to that scoring rule. And the way this is going to work is by looking. So go back to this. What's going to end up happening is that if I violate coherence, say by, imagine that goes through the origin. So I'm not subject to sure loss, but I'm not a closed convex cone. Then there is going to be some closed convex cone such that nudging this original one in the direction of that closed convex cone is guaranteed to increases accuracy in both worlds. So what we're looking at here is really what the proof does is it proves that there's that it's locally dominated in the sense that there's something nearby, a little nudge that you can make to it that would improve accuracy. So what we're really trying to find here is we're looking at the first variation of these two functionals. And we're trying to find some G such that the first variation, some G that corresponds to a closed convex cone such that nudging it in that direction, well, the derivative is negative, which is going to end up guaranteeing that a little shift in that direction is guaranteed to increase accuracy or decrease in accuracy. Okay, I mean, so that's more or less how it works. It's, I mean, for those that are interested, I can send along proof notes. One thing to bear in mind, though, is that this does not guarantee that coherent things are not dominated. But what we can show is that for every coherent set of almost desirable gambles, there is some way to set these coefficients, which sort of roughly corresponds to how much you care about type 1 and type 2 error. There's some scoring rule that renders that coherent thing non-dominated. So the asymmetry between coherence and incoherence is this. Incoherent sets of almost desirable gambles, they're dominated on every scoring rule, on every inaccuracy measure. Coherent things, there is some inaccuracy measure, some way of prioritizing type 1 and type 2 error such that your coherent set of almost desirable gambles is non-dominated relative to that scoring rule. So this tells you how to, this tells you which scoring rule it is non-dominated with respect to. And this spans the whole set of coherent sets of almost desirable gambles. We can always find, for any coherent one, we can always find one that does that. Okay, so I will leave it there since we're way over time. Just to highlight, I think, where we've landed, whether or not you think there was any shortcoming in our approach to theorizing about coherence before, this, I think, provides, or when suitably generalized, provides a fuller picture of our reasons to want to make coherent judgments of desirability. It also settles some questions that other people have been interested in. So Brandon Feitelson, for example, for a while was looking at accuracy dominance arguments for probabilistic representability for comparative belief relations. This settles that question, it uses a different class of scoring rules. So we can use this same argument to show that almost preference relations should be representable by a set of probabilities on pain of accuracy dominance. I think it also, in particular, proposition 4 is the key to understanding why the impossibility results for IP scoring rules, which originally by Teddy Seidenfeld, and then other people, Connor Mayer Wilson and Greg Wheeler and Miriam Schoenfeld have discussed these, and others as well. I think proposition 4 is the kind of key to understanding why those aren't particularly problematic, but we can talk about that more. And then there are a bunch of generalizations that we need to do for this argument to really be compelling, but hopefully it's a good first step. So I'll stop there.